This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss about question bank on module 4, which is magnetic and superconducting materials. So in this presentation, I will discuss part A, which is analytical questions on module 4. So the first question is calculate magnetization and magnetic flux density if magnetic field intensity is 250 amperes per meter and relative permeability is 50. Okay. So solution. So they have given us the magnetic field intensity and relative permeability, right? So given magnetic field intensity H is 250 amperes per meter and relative permeability mu r is 50. So we need to calculate magnetization. So magnetization M is equal to chi into H. Right, H is magnetic field intensity and chi is susceptibility and M is magnetization. But what they have given here only relative permeability. We do not know what is the value of chi. So we can write chi in terms of relative permeability. Okay, so mu r, relative permeability mu r is defined as 1 plus chi. Okay, so from this equation we can write down chi as mu r minus 1. Okay, so we are going to substitute this chi in this equation. So M will be mu r minus 1 into H. Okay, so we know the values of mu r and H, so we can substitute the values. So M is equal to mu r is 15, 15 minus 1 into H is given as 250. So the answer is 3500 amperes per meter. So this is the magnetization we have calculated. Next we need to calculate magnetic flux density. Magnetic flux density is B. So B is mu into H, right? So yeah, so we do not have mu, but we have mu r, right? So we know that mu is actually equal to mu naught into mu r. So we are going to substitute this mu naught and mu r in this equation. So B is equal to mu naught into mu r into H. Okay, so mu naught we know it's a constant, 4 pi into 10 power minus 7. And mu r is given as 15 and H is given as 250. So we'll get the answer to the magnetic flux density B as 0.00471 Gas. So these are the two parameters we have calculated. Magnetization and we have calculated magnetization and magnetic flux density given magnetic field intensity H and relative permeability. Okay, so we have used two equations basically. B is equal to mu H and M is equal to chi H, but we do not have the mu value and chi value directly. So we have used mu r is equal to 1 plus chi, from which we have calculated what is chi, and then for this we have used mu is equal to mu naught into mu r, and then we substituted mu as mu naught into mu r. Mu naught is a constant, permeability of free space. We know the value of permeability free space, so then we got substituted the values of mu naught and mu r, and H we got the value of magnetic flux density. Okay, yeah. So let us go to the next question. The next question is find relative permeability if magnetic field is 220 amperes per meter and magnetization is 3300 amperes per meter. Okay. So we need to calculate relative permeability. Okay, so what they have given us as inputs, they have given magnetic field H as 220 amperes per meter and magnetization M as 3300 amperes per meter. Okay, so we know we need to calculate relative permeability mu r. Okay, so we know that mu r is equal to 1 plus chi. 1 plus chi is susceptibility. And from the equation of M, magnetization M is equal to chi into H. We can write down what is chi. Chi is basically M by H. So we are going to substitute this here, so that will become 1 plus M by H. Okay. So substitute the value mu r is equal to 1 plus M by H, because 1 plus chi actually, but chi is M by H. So we have substituted that. So 1 plus M is at 3300 and H is 220. Okay. So the relative permeability is 60. Okay. So we have calculated the relative permeability given magnetic field and magnetization using the equation mu r is equal to 1 plus chi. And we have also used M is equal to chi H. So chi is equal to M by H. So we have substituted in this equation to get what is mu r, because they have given inputs as H and M. Okay. So let us go to the next problem. The magnetic susceptibility of aluminum is 2.3 into 10 power minus 5. Find its permeability and relative permeability. So they have given us susceptibility chi, which is 2.3 into 10 power minus 5. We need to find out permeability mu and relative permeability mu r. So these two we need to calculate. Okay. So we know the relation equation or relation between mu r and chi. So mu r is equal to 1 plus chi. So we can directly substitute in this equation 1 plus 2.5 into 10 power minus 5. Okay. So that is what is the answer. So mu r is actually equal to 1.00002. Okay, so that is mu r. Next one we need to find out. So this is not just 2.3 plus 1, 3.3. This is actually 1 plus 0.00002. That is why we get this 2, 3. Okay, see 1.0002. Okay, so next what we need to find out? Relative permeability we have calculated, and then we have to find out permeability, which is mu naught into mu r. So mu naught we know 4 pi into 10 power minus 7, and mu r is this value 1.00002. Okay, so the value of mu is into 10 power minus 7 Henry per meter. So this is the value of 12.56 into 10 power minus. Okay. So we have calculated relative permeability and permeability given susceptibility using the equation of mu r is equal to 1 plus chi and mu is equal to mu naught into mu. Okay. So let us go to the next problem. If a magnetic field of strength 300 amperes per meter produces a magnetization of 4200 amperes per meter in a ferromagnetic material, find the relative permeability of the material. So we need to find out the relative permeability given magnetic field and magnetization. Okay, so that is the question. So they have given us that magnetization is 4200 amperes per meter and magnetic field strength is 300 amperes per meter. We need to calculate mu r. Okay, so we know the relation between mu r and 1 chi, right? But okay, mu r is equal to 1 plus chi, but m, the magnetization m is given as chi into h. Okay, so chi is m by h. Okay, so in this equation 1 plus m by h. So substitute the value mu r is equal to 1 plus m by h. So we are going to find out 1 plus m is 4200 divided by 300. So the value of mu r is 50. Okay. So again we have used this equation mu r is equal to 1 plus chi and m is equal to chi into h. Okay. So this equation we have been using in most of the problems, right? So let us go to the next problem in magnetic materials. The paramagnetic material has a magnetic field intensity of 104 amperes per meter. The susceptibility of the material at room temperature is 3.7 into 10 power minus 3. calculate the magnetization and magnetic flux density. So we need to calculate magnetization and magnetic flux density. They have given us the magnetic field intensity H is 104 amperes per meter, and susceptibility also they have given, which is 3.7 into 10 power minus. So we need to calculate magnetization. Magnetization M is equal to chi into H. This is the direct formula, so we can substitute the value of chi, which is 3.7 into 10 power minus 3 into 104. We will get the magnetization, which is 0.38. So M is 0.384 amperes per meter. So magnetization, and then we need to calculate magnetic flux density B. Okay. So B is equal to mu into H. B is equal to mu into H. Here, so calculate the magnetic flux density B, and we have the value of H, and we need mu, right? So we do not have mu, but we can calculate, we can use the equation of mu is equal to mu naught into mu r, but we also do not have mu r, but mu r we can write because chi we have, so 1 plus chi is mu r, so 1 plus 3.7 into 10 power minus 3, so that is mu r. Then we are going to substitute this in this equation of B. So B is equal to mu naught, which is 4 pi into 10 power minus 7, and mu r, which is 1 plus 3.7 into 10 power minus 3 into H. H is given as 104. Okay. So then we will find out, we will find out B as 1.31 into 10 power minus 4 Tesla. Okay. So we have to be careful here. 1 plus 3.7 into 10 power minus 3, right? So you have to write 0.0037 in 1 plus 0.0037, then it will be 1.0037. Then multiply with 104, and then multiply with 4 pi into 10 power minus 2, where phi is 3.14. Okay. So then we will get the answer B as 1.31 into 10 power minus 4 Tesla. Yeah. So this is the fifth problem, and this is the last problem in magnetic materials. And then we will discuss the problems in superconducting materials. Okay. So let us start the problems on superconducting materials. So that will be the sixth one. Okay. So the sixth problem is the transition temperature for lead is 7.2 Kelvin. However, at 5 Kelvin, it loses the superconducting property if subjected to a magnetic field of 3.3 into 10 power 4 amperes per meter. Find the maximum value of H, which will allow the metal to retain its superconductivity. So we need to find the maximum value of H. Okay. So given, so whatever they have given us the transition temperature Tc, which is 7.2 Kelvin, and they've also given us the magnetic field H. So that is Hc is 3.3 into 10 power 4 amperes per meter. So we need to calculate the value of H at 0 Kelvin. So Hc naught we have to calculate. So this is Hc of T. We do not know what is the field maximum value of H, which will allow the metal to retain its superconductivity at 0 Kelvin. Hc of 0 or H naught. You can say it is H naught or Hc of 0. Okay. So yes. Okay. So we need to calculate that. So the equation between this H and Tc is H of T. H of T is H of 0 into, okay, so you can write this as H of T and H of 0. H of 0 into 1 minus T square by Tc square. So this is the relation between H of T and H naught. So from this equation, what we need to calculate? We need to calculate H of 0, maximum value of H at 0 Kelvin. Okay. So they have given us H of T, right? the magnetic field, superconducting property of the magnetic field is subjected to this. Okay, so H of T is given. Okay, 5 Kelvin, we have H of T as 3.3, so we need to calculate H of 0. So H of 0 is H of T divided by 1 minus T square by Tc square. So I just want this, so I have taken this left hand side, so then I got this. So substitute the values of H of T is this. Okay, so 3.3 into 10 power 4 divided by 1 minus T square. T is 5 square. Tc is so transition temperature is 7.2 Kelvin. So 7.2 whole square. Okay. So when we do all these values, what do we get is 6.37 into 10 power 4 amperes per meter. 6.37 into 10 power 4 amperes per meters is the H of 0. The maximum value of H at 0 Kelvin is 6.37 into 10 power 4 amperes per meter. Yeah. So we have basically used this equation. So Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. So this is the formula. Right. So using this formula, we want Hc of 0. So we want Hc of 0. So then Hc of 0 will be Hc of T divided by 1 minus T square by Tc square. So they have mentioned transition temperature. So the transition temperature Tc is 7.2 Kelvin, and the T at which it is going to lose its superconducting property. So the T is 5K and field is 3.3. So that is Hc of T is 3.3 into 10 power 4. So substituting all the values, we found out that the Hc of 0 is 6.37 into 10 power 4 amperes per meter. Let us go to the next problem. So the next problem is the critical field of niobium is 1 in 10 power 5 amperes per meter at 8 Kelvin and 2 into 10 power 5 amperes per meter at 0 Kelvin. Calculate the transition temperature of the element. Okay. So yeah. So how do we need to calculate the transition temperature? So what they have given us is that critical field of niobium, Hc of T, T is finite at 8 Kelvin is 10 power 5 amperes per meter. Okay, so the T is basically 8 Kelvin and 2 into 10 power 5 amperes per meter at 0 Kelvin. So Hc of 0 is 2 into 10 power 5 amperes per meter, and T is so this is a T is equal to 0. Fine. Okay. So we need to calculate Tc. So right. So we know the formula between T and Tc. So it's Hc and Tc and T, right? So Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. So this is the formula. We need this formula. So using this formula, we are going to write this equation. We need to calculate Tc, right? So yeah, so we need to calculate Tc. So 1 minus T square by Tc square is equal to, we want this, so I am going to write it as Hc of T divided by Hc of 0. Okay. Next, I am going to take this side, I am going to make that side. So 1 plus Hc of T divided by Hc of 0 is equal to T square by Tc square. Now, I want actually Tc square. So Tc. So Tc square is equal to T square by 1 plus Hc of T divided by Hc of 0. We want Tc, not Tc square. So Tc will become square root, or for all of that we can write square root, or so T square divided by 1 plus Hc by Hc naught, Hc of 0, this is Hc of T whole power 1 by 2. Okay, or you can take out this, or you can simply write it as Tc is equal to T by square root 1 plus Hc of T divided by Hc of 0, because T square and power 1 by 2, so that will become T. Okay, substituting all the values. So T is what? T is 8 Kelvin, so 8 divided by square root 1 plus Hc. Hc of T is 10 power 5 divided by Hc of 0, 2 into 10 power 5. So doing all these, we will get Tc as 11.3 Kelvin. Okay, so this is the equation we got. So Tc is equal to T divided by square root 1 plus Hc of T divided by Hc of 0. So then we have substituted all the values. T is given and Hc of 0 is given. Hc of T is given. Okay. So remember, to avoid the confusion, critical field of niobium is 1 into 10 power 5 amperes for 8 Kelvin. 8 Kelvin is finite. So T is finite. So you should take this as Hc of T and then 2 into 10 power 5 amperes per meter at 0 Kelvin. So that is Hc of 0. Field at 0 Kelvin. So whatever this is T. T is equal to 0 is this. At finite value of T is equal to 8 Kelvin is this. Okay. So we got the Tc as 11.3 Kelvin. Okay, let us go to the next problem. So this relation is very important, that between Hc of T and Hc of 0 and Tc. So this equation we are going to use it in many ways to find out Tc, to find out Hc of 0. We can directly find out Hc of T, right? So if you know this equation, you can calculate various parameters using this equation. Okay. Okay, so let us go to the next one. The critical field at 5 Kelvin is 2 into 10 power 3 amperes per meter in a superconductor ring of the radius 0.02 meters. Find the value of critical current. Okay, so we need to find the value of critical current, and whatever they have given is, they have given us magnetic field at 5 Kelvin. So Hc of T is given as 2 into 10 power 3 amperes per meter, and they have also given our radius. Radius are also given as 0.02 meters. We need to calculate critical current. Okay, so critical current IC is equal to 2 pi R into Hc. So R is radius. So if you want, you can use small r or capital R, whatever you want. R into Hc of T. So this is the formula, 2 pi R into Hc. So we know what is radius. Radius is given and Hc is given. Just need to substitute 2 into pi value 3.14 into R is 0.02 into Hc is 2 into 10 power 5. Okay. Substitute all the values. We are going to get IC as 251.4 amperes. Okay, so that is the answer. Current, right? So the critical current is 251.4 amperes. So we have used this formula. IC, critical current IC is 2 pi R into Hc, where R is radius and Hc is the critical field. Okay, yeah. So let us go to the next problem. Next problem is, the superconducting tin has critical temperature of 3.7 Kelvin at 0 magnetic field and critical field of 0.0306 Tesla at 0 Kelvin. Find the critical field at 2K. Find the critical current also if radius is 1 meter. So whatever they have given, so they have given us critical temperature Tc is 3.7 Kelvin and the critical field Hc of T and critical field at 0 Kelvin. So that is Hc of 0. Hc of 0 is 0.0306 Tesla. Critical temperature at 0 magnetic field. Now we need to calculate. First, we need to calculate critical field at 2 Kelvin. Okay, so T is given as 2 Kelvin. First, we need to calculate critical field. So, Hc of T is equal to Hc of 0 into 1 minus T square divided by Tc. Substitute all the values. Hc of 0 is 0.0306 into 1 minus T square is 4. 2 square is 4. Tc square is 3.7 square. So, better this also we make it as square. 2 square. Okay, so maybe I will write it. Hc of 0 is 0.0306 into 1 minus 2 square divided by 3.7 whole square. Okay. So that is 3.7 whole square. So this is Hc of T. We will get as 0.0216 field amperes per meter. Okay. So the critical field at 2 Kelvin is 0.021 amperes per meter. Next, we need to calculate critical current. IC is 2 pi R into H. So 2 into 3.14 into radius is given as 1 meter into Hc is from 0.0216. So substituting all the values, we are going to get IC as 0.136 amperes. Okay. So we have calculated critical field and critical field at finite temperatures and critical current. Okay, given critical field. So let us go to the next problem. So that is the last problem in this module 4, and then we will look at the long answer questions of this. So the last one is calculate the critical current for a wire of lead having a diameter of 1 millimeter at 4.2 Kelvin. The critical temperature for lead is 7.18 Kelvin and Hc of 0 is given 6.5 into 10 power 4 amperes per meter. Okay. First, they have given us diameter, they have given, not radius. Now here they have mentioned as diameter. Diameter is 1 millimeter. So 1 into 10 power minus 3 meter. So if we want radius, from this we are going to calculate radius, which is 10 power minus 3 by 2 in meters. So that is radius. Okay, fine. And temperature is given. Temperature is given as 4.2 Kelvin. The critical temperature for lead, so Tc is 7.18 Kelvin and Hc of 0 is also given 6.5 into 10 power 4 amperes per meter. So we need to calculate critical current. Okay, so critical current, to calculate critical current IC, the formula is 2 pi R into Hc. So we need Hc. We do not have Hc. So first we need to calculate Hc. Okay. So Hc of T is Hc of 0 into 1 minus T square by Tc square. So Hc of 0 is given 6.5 into 10 power 4. 1 minus T is given as 4.2 square. Tc is given as 7.18 square. So we'll get the value of Hc of T as 42.7 into 10 cube amperes per meter. Once we have Hc of T, we are going to substitute this Hc of T in this equation. So Ic is 2 pi R into Hc. Okay, so 2 into 3.14 into R is 10 power minus 3 by 2 into 42.7 10 cube. Okay, so the current IC is 134.2 amperes. 132.4. Okay, so we have calculated the critical current. To calculate critical current, first we have calculated critical field. Once we have calculated critical field, we have substituted critical field in the equation of current to get the critical current. Okay. Yeah. So we have basically solved all the 10 problems. 5 of them are on magnetic materials and 5 of them are on superconducting materials. Okay. So We have solved all the 10 problems on numerical problems on module. Okay. So these are the textbooks I have used and references to look at. And to summarize, I have discussed the analytical questions of module 4 in this presentation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.